There is something you should know about space, something that contradicts what you may have learned. Space is not entirely silent. This is not a trick of language or a philosophical claim about the nature of existence. It is a measurable, scientific truth that unfolds across distances so vast they reshape our understanding of sound itself. Right now, as you settle into wherever you are, electromagnetic waves are traveling through the cosmos at frequencies that, if translated into audible tones, would fill the universe with a symphony unlike anything composed on Earth. These are not sounds in the way we typically understand them. You could not hear them if you floated freely in the vacuum between stars. But they exist nonetheless, carried by plasma and magnetic fields, by the very fabric of space shaped by gravity and energy. They are the vibrations of existence itself, and through the work of scientists and their instruments, we have found ways to listen. This is a journey through those sounds, through the mechanisms that create them and the technologies that reveal them. It is a journey that moves slowly, methodically, through fact after fact, each one grounded in observation and measurement. There will be no urgency here, no rushing toward conclusions. Instead, we will move at the pace of discovery itself, allowing each concept to settle before we move to the next. You may listen until sleep arrives, or you may listen simply to know. Either choice is perfectly suited to what follows. What we call space sounds emerge from a precise scientific process. Space itself, the vacuum between celestial bodies, cannot transmit pressure waves as Earth's atmosphere does. Sound waves, as we experience them, require molecules to bump into one another, transferring energy through compression and rarefaction. In the near-perfect vacuum of space, with perhaps only a few particles per cubic centimeter, this traditional mechanism fails completely. And yet, space is filled with charged particles, electrons, and ions that interact through electromagnetic forces across enormous distances. These interactions create waves, not of pressure, but of electric and magnetic fields, oscillating in patterns that can be measured, analyzed, and in some cases, converted into audible frequencies. The conversion process is called sonification, and it is both an art and a science. When spacecraft instruments detect these electromagnetic waves, they record variations in frequency, amplitude, and polarization. Some of these waves occur naturally at audio frequencies between 20 Hz and 20,000 Hz, the range of human hearing. Others occur far below or far above this range. For those that fall outside audible bounds, scientists can shift the frequencies up or down, maintaining the relationships between different tones while bringing them into a range our ears can process. This is not fabrication. It is translation, a way of experiencing data through a different sensory channel. The instruments that make these observations are remarkably sensitive. They consist of long wire antennas extending from spacecraft, electric field sensors that measure voltages across precise distances, and magnetometers that detect minute variations in magnetic field strength. When plasma waves wash over these instruments, they create measurable signals that can be recorded, stored, and later converted into audio files. The Voyager spacecraft, launched in 1977, carried such instruments. So did Cassini, Juno, and the twin Van Allen probes that studied Earth's radiation belts. Each mission has contributed unique recordings to our growing library of cosmic sounds. What makes these sounds particularly suited to relaxation is their origin in natural processes that operate on scales beyond human comprehension. There is no human emotional content in the oscillation of a plasma wave. No anxiety, no urgency, no narrative arc designed to manipulate your attention. These are simply the fundamental behaviors of matter and energy in space, translated into a form we can perceive. They are, in their essence, neutral. They exist whether we listen or not, whether we understand them or not. This neutrality, this absence of intentional emotional content, creates a unique listening experience that many find deeply calming. The journey ahead will take us to the sun, where sound waves larger than Texas ripple through the star's interior. We will visit Earth's magnetosphere, where electrons create whistling choruses at dawn. We will follow Voyager into interstellar space, listening to the sounds of plasma beyond the influence of our sun. We will hover near Jupiter and Saturn, massive planets whose magnetic fields generate radio emissions powerful enough to be detected across the solar system. We will experience the sounds of black holes, not as Hollywood might imagine them, but as they truly manifest through the ripples they create in surrounding gas. And we will hear the gentle sounds of wind on Mars, recorded by rovers standing on another world's surface. Each section will build on the one before it, gradually expanding your understanding of how sound manifests in space, how scientists detect and study it, and why these sounds carry properties that many find conducive to rest. There is no need to remember every detail. The information will be here, stable and unchanging should you wish to return to it. For now, simply allow the words to wash over you, carrying facts and context in a steady, unhurried flow. To understand space sounds, we must first understand plasma, the fourth state of matter. On Earth, we are most familiar with solids, liquids, and gases. But in the universe as a whole, plasma dominates. Stars are made of plasma. The vast spaces between stars contain tenuous plasma. Even the regions around planets, including Earth, are filled with plasma of varying densities. Plasma forms when gas becomes so hot, or when it encounters such intense radiation that electrons are stripped from atoms, creating a mixture of positively charged ions and freely moving electrons. This mixture behaves differently from ordinary gas. Because plasma particles carry electric charge, they respond to electric and magnetic fields. They can conduct electricity. They can generate magnetic fields of their own. And, critically, they can support the propagation of various types of waves that simply cannot exist in neutral gas. These waves are the source of most space sounds. The simplest plasma wave is the electron plasma oscillation. Imagine a volume of plasma where electrons are slightly displaced from their equilibrium positions, perhaps by a passing disturbance. The positively charged ions, being much more massive, barely move. The displaced electrons feel a restoring force from the electric field created by the charge separation. They accelerate back toward their equilibrium positions, overshoot due to their momentum, and begin oscillating back and forth. The frequency of this oscillation depends on the electron density. The denser the plasma, the higher the frequency. This fundamental frequency, called the electron plasma frequency, serves as a characteristic signature of the plasma environment. In Earth's magnetosphere, plasma densities vary from a few electrons per cubic centimeter in the outer regions to several thousand per cubic centimeter in the plasmasphere, the dense torus of cold plasma surrounding Earth. These densities produce plasma frequencies ranging from a few hundred hertz to tens of kilohertz, frequencies that fall comfortably within or near the range of human hearing. When instruments detect oscillations at these frequencies, the resulting audio files sound like tones of various pitches, sometimes pure, sometimes complex, and changing. Another important class of plasma waves involves magnetic fields. When a magnetic field permeates a plasma, it adds structure to how particles can move and how waves can propagate. Alfvén waves, named after physicist Hannes Alfvén, are one such type. These waves travel along magnetic field lines, carrying energy through the plasma much as waves travel along a stretched string. The velocity of alpha waves depends on the magnetic field strength and the plasma density. In the dense plasma near Earth, they travel at hundreds of kilometers per second. In the more tenuous plasma of the outer magnetosphere or interstellar space, they can move at thousands of kilometers per second. Whistler mode waves represent another category. These electromagnetic waves can propagate through magnetized plasma, and they have a distinctive property. Different frequencies travel at different speeds. Higher frequencies travel faster than lower frequencies. This dispersion means that if a burst of electromagnetic energy containing many frequencies enters the plasma, the signal spreads out over time as it travels, with higher frequencies arriving first and lower frequencies arriving later. When converted to audio, this creates a descending tone, like a whistle falling in pitch, hence the name. Whistler mode waves were actually first detected on Earth in a curious way. In the late 19th and early 20th centuries, telephone engineers sometimes heard strange whistling sounds on long-distance telephone lines, particularly during and after thunderstorms. These were lightning-generated electromagnetic signals that had traveled up into the magnetosphere, followed magnetic field lines to the opposite hemisphere, and then returned to Earth, the dispersion occurring during their journey through space. Modern spacecraft now detect Whistler mode waves directly in space, and they play important roles in accelerating particles in radiation belts and producing various audible phenomena. Ion acoustic waves provide yet another mechanism. In these waves, ions and electrons oscillate together, but the electrons, being much lighter, respond more quickly to changing electric fields. The result is a wave that propagates at the speed of sound in the plasma, but it is not the same as sound in air. The restoring force comes from electric fields rather than pressure, and the wave can exist in the near vacuum of space. Ion acoustic waves typically have frequencies from hundreds of hertz to several kilohertz, well within the audible range. When spacecraft detect these waves, the resulting audio can sound like rushing water or wind, though it is neither. Radio waves represent the highest frequency electromagnetic emissions commonly discussed as space sounds. Unlike plasma waves, which require the presence of plasma to propagate, radio waves can travel through vacuum. They are produced when charged particles are accelerated, particularly electrons spiraling along magnetic field lines or electrons participating in cyclotron resonance. Jupiter, Saturn, and Earth all produce natural radio emissions through these processes. The frequencies range from tens of kilohertz to tens of megahertz. The lower frequency emissions fall just above or within the extended range of human hearing, while higher frequencies must be shifted downward to become audible. The cyclotron maser instability is a key mechanism for producing intense radio emissions. It occurs when a population of energetic electrons is slightly displaced from its equilibrium, creating conditions where electron motion can amplify electromagnetic waves at frequencies near the electron cyclotron frequency. This frequency depends on the local magnetic field strength according to a simple relationship. The frequency equals the electron charge times the magnetic field strength divided by 2 pi times the electron mass. This means that stronger magnetic fields produce higher frequencies, and the emissions from different altitudes in a planetary magnetosphere will have different characteristic frequencies. When scientists convert these electromagnetic phenomena into audio, they make careful choices about how to map the data. For sonifications of images from telescopes, brightness might be mapped to volume, with brighter sources producing louder tones. Position might be mapped to pitch, with higher locations in an image producing higher notes. For time series data from spacecraft instruments, the process is more direct. The measured electric or magnetic field variations are simply played back, either at their original frequencies if those fall in the audible range, or shifted to audible frequencies if they do not. In some cases, data is sped up or slowed down to compress long-duration events into shorter audio clips, or to bring very low frequencies into hearable range. The result is that we can experience electromagnetic phenomena as sound, gaining insight into processes that would otherwise remain purely abstract. A sudden burst of plasma waves becomes a chirp or hiss. A steady oscillation becomes a tone. The complex turbulence of the solar wind becomes something like static, but with structure and variation that reveal underlying physical processes. This translation from electromagnetic to acoustic is not arbitrary. The mathematics describing wave propagation is the same whether the waves are sound waves in air or electromagnetic waves in plasma. Frequency, wavelength, amplitude, phase, these concepts apply equally to both. The primary difference is the medium through which the waves travel and the forces that provide the restoring mechanism. In air, it is pressure. In plasma, it is electromagnetic force. But the wave behavior follows similar patterns, which is why the auditory experience of space sounds can feel familiar even as it represents something fundamentally alien. One particularly important aspect of space sounds is their variability. Unlike manufactured tones, which remain constant and predictable, natural electromagnetic waves fluctuate in response to changing conditions. The plasma density changes as a spacecraft moves through different regions. The magnetic field strength varies. Particles with different energies come and go. All of these factors influence the waves being generated and detected. The result is that space sounds have an organic, evolving quality. They rise and fall. They change in character. They surprise you with sudden bursts or long, slow modulations. This variability, this sense of experiencing something genuinely happening rather than something pre-programmed, contributes to their appeal for relaxation and sleep. Consider the bandwidth of these signals. Bandwidth refers to the range of frequencies present at any given time. A pure tone has essentially zero bandwidth, all the energy concentrated at a single frequency. White noise has infinite bandwidth, energy spread equally across all frequencies. Space sounds typically fall somewhere in between. A chorus of Whistler mode waves might span several kilohertz, creating a rich, complex sound. Saturn's kilometric radiation can produce narrow-band tones with bandwidths as small as 200 Hz, alongside broader emissions. This mix of narrow and broad spectral features creates auditory textures that are neither monotonous nor chaotic, a balance that many find particularly suitable for extended listening. The instruments that detect these waves operate continuously. They sample the electric and magnetic fields many times per second, building up detailed records of how these fields change over time. The Cassini spacecraft's radio and plasma wave science instrument, for example, could measure electric fields from 50 Hz to 40 MHz and magnetic fields from 50 Hz to 20 kHz. It did this throughout its 13 years orbiting Saturn, accumulating an enormous dataset of electromagnetic wave observations. Similar instruments on other spacecraft have created comparable archives. The result is that we now have decades worth of space. Sounds from various locations in the solar system and beyond, a library that continues to grow with each new mission. Understanding the physics behind these sounds deepens the experience of listening to them. Each tone, each fluctuation, represents a real physical process. An increase in pitch might indicate a spacecraft moving into a region of stronger magnetic field. A sudden burst might correspond to an injection of energetic particles from a magnetic reconnection event. A slowly changing whistle might trace the motion of a plasma density boundary. The sounds are not random. They are structured by the laws of physics, by the geometry of magnetic fields, by the distribution of particles and energy in space. This structure, even if not consciously analyzed while listening, gives the sounds a coherence that purely random noise would lack. Moreover, the scales involved are profoundly calming to contemplate. The plasma through which these waves propagate extends across millions or billions of kilometers. The magnetic field lines along which they travel connect planets to their moons or stretch out into the interstellar medium. The energy driving these processes comes from stellar fusion, from planetary rotation, from the solar wind. These are not human scales. They are cosmic scales, and experiencing them through sound provides a unique form of perspective, a reminder of the vast indifference of the universe to our daily concerns. The sonification process, for all its technical sophistication, has a simple goal: to make the invisible accessible. Electromagnetic waves invisible to our eyes become audible to our ears. Data that would otherwise exist only as numbers in a spreadsheet becomes experiential, something we can feel and respond to directly. This accessibility has practical value for scientists who can sometimes identify patterns in audio that might be missed in visual displays. But it also has value for anyone seeking to understand and appreciate the universe, or simply to find calming ambient sound divorced from terrestrial origins and meanings. The Sun, our nearest star, is in a constant state of vibration. The entire star rings like a bell, not with a single tone, but with millions of distinct resonant modes, each corresponding to a different pattern of oscillation coursing through the solar interior. The study of these oscillations is called helioseismology, and it has revolutionized our understanding of the Sun's internal structure, rotation, and dynamics. More importantly, for our purposes, it provides one of the most direct examples of how sound exists in space, albeit at frequencies far below human hearing. Sound waves in the Sun are fundamentally similar to sound waves in Earth's atmosphere. They are pressure waves, compressions, and rarefactions traveling through a medium. The difference is scale. In air, sound waves might have wavelengths of centimeters to meters. In the Sun, sound waves have wavelengths measured in thousands of kilometers. Their periods, rather than milliseconds to seconds, extend to minutes. The most prominent oscillations have a period of about 5 minutes, meaning that if you could watch a point on the Sun's surface, you would see it rise and fall with this characteristic rhythm. These oscillations are excited by turbulent convection in the outer third of the Sun. Near the surface, the Sun's temperature has dropped to the point where atoms can hold onto some of their electrons, increasing the opacity of the gas. This traps heat trying to escape from deeper layers, and the only way for that heat to move outward is through convection, the bulk motion of hot gas rising and cool gas sinking. This convective layer is called the convection zone, and it extends from about 200,000 kilometers below the visible surface down to a depth of about 200,000 kilometers, about 30% of the Sun's radius. Within the convection zone, enormous cells of hot plasma rise toward the surface, cool by radiating energy into space, and sink back down. The largest of these convection cells, called supergranules, are about 30,000 kilometers across, roughly twice the diameter of Earth. Smaller granules, a few thousand kilometers across, create the mottled appearance of the solar surface when viewed at high resolution. The turbulent motions within and between these convective cells generate acoustic noise, random pressure fluctuations that propagate as sound waves throughout the Sun. Most of these sound waves dissipate quickly, their energy absorbed or scattered. but certain frequencies, certain wavelengths, match the natural resonances of the sun's structure. When this happens, the waves reinforce themselves, building up into standing waves that can persist for days or weeks. These are the solar oscillation modes, and they come in many varieties, classified by how they divide the sun's surface into regions of upward and downward motion. The classification uses three numbers. The radial order, denoted N, indicates how many nodes the wave has in the radial direction, how many layers at different depths are momentarily stationary as the wave oscillates. The spherical harmonic degree, denoted L, describes the number of node lines on the surface. Low L modes have few divisions, with large areas of the surface moving up and down together. High L modes have many divisions, with small patches moving in opposite directions. The azimuthal order, denoted M, describes the east-west pattern of these divisions. Together, these three numbers uniquely identify each mode, and there are millions of possible combinations. The strongest modes have radial orders around 14 and spherical harmonic degrees between a few and a few hundred. Their frequencies cluster around 3 MHz, or about 5-minute periods. The velocity amplitudes of these oscillations at the surface are tiny by human standards, on the order of 1 centimeter per second, slower than you walk. The relative brightness variations are even smaller, about 1 part in 10 million. Yet these minute oscillations, measured precisely from Earth and from spacecraft, carry detailed information about conditions hundreds of thousands of kilometers below the surface. The speed of sound in the sun depends on temperature and composition. Hotter gas supports faster sound waves. Gas with more heavy elements, more opacity, supports slower sound waves. As sound waves travel through the sun, they refract, bending due to the changing sound speed with depth. Waves that penetrate deeper into the sun, where temperatures are higher, travel faster at depth and curve back toward the surface more steeply. Waves confined to the outer layers take longer to complete their oscillation cycles. By measuring the precise frequencies of millions of modes, scientists can invert the data to determine how sound speed varies with depth throughout most of the solar interior. This inversion process is mathematically complex, but the principle is straightforward. Different modes penetrate to different depths, so they sample different regions of the sun. By comparing the frequencies of modes that penetrate deeply with those that stay near the surface, scientists can build up a picture of internal structure. The results have been remarkably precise. Helioseismology has determined the depth of the convection zone to within a few hundred kilometers out of a total solar radius of nearly 700,000 kilometers. It has revealed how the sun rotates at different depths and latitudes. It has tested and refined theoretical models of stellar structure. The rotation profile is particularly interesting. At the surface, the sun rotates differentially, with the equator completing a rotation in about 25 days and the poles taking about 35 days. Helioseismology shows that this differential rotation persists throughout the convection zone. But deeper, in the radiative zone where energy transport occurs via radiation rather than convection, the rotation becomes uniform, the same at all latitudes. The transition between these two regimes occurs in a thin layer called the tachocline, where strong shearing motions are believed to generate the sun's magnetic field. If we could hear these oscillations directly, what would they sound like? The strongest modes, with frequencies around 3 MHz, are 57 octaves below the lowest note on a piano. To bring them into the audible range, scientists speed up the time series data by enormous factors, 42,000 times or more. When this is done, the sun produces a complex evolving tone, rich with harmonics. It is not a single pure note, but a chord, with many frequencies present simultaneously. The sound rises and falls as different modes come in and out of phase, as some modes grow stronger and others weaken. The Global Oscillation Network Group, or GONG, operates 6 telescopes placed around Earth to observe the Sun continuously. Because the Sun sets at each location, a single telescope cannot provide uninterrupted observations. But with telescopes in California, Hawaii, Chile, the Canary Islands, India, and Australia, at least one always has the Sun above its horizon. This global network has been operating since the 1990s, accumulating decades of continuous solar oscillation data. The result is an unprecedented understanding of how the Sun vibrates and how those vibrations change over time. There are subtle variations in the mode frequencies over the 11-year solar cycle. As the Sun's magnetic activity waxes and wanes, the mode frequencies shift slightly, typically by a few parts per million. The shifts are larger for modes that are more strongly affected by magnetic fields, providing insight into how magnetism perturbs the oscillations. There are also variations on shorter timescales, perhaps associated with the rotation of active regions into and out of view, or with changes in the convection zone structure. The Solar and Heliospheric Observatory, SOHO, a spacecraft positioned between Earth and the Sun where gravitational forces balance, has provided even more precise helioseismology data. Free from the blurring effects of Earth's atmosphere, SOHO can resolve individual mode frequencies with extraordinary precision. It has observed over 250,000 individual modes, and scientists expect that, eventually, over 1 million modes will be identified. Each mode provides a slightly different probe of the solar interior, and together they create a detailed 3-dimensional map of conditions inside the star. Local helioseismology extends the technique to study features on the solar surface and just below it. Rather than analyzing global modes, local helioseismology tracks how acoustic waves travel between different points on the surface. The travel time of these waves depends on the sound speed along their path, which in turn depends on temperature and flows beneath the surface. By measuring travel times between many pairs of points, scientists can map subsurface temperature variations, detect flows beneath active regions, and even image the far side of the Sun, the hemisphere facing away from Earth. This far-side imaging works because some acoustic waves travel deep enough to cross from the visible hemisphere to the far side and back, their travel times affected by active regions on the far side. By analyzing patterns of travel time variations, scientists can create maps of active regions on the far side of the Sun 24 to 48 hours before they rotate into view. This has practical applications for space weather forecasting, as it provides advance warning of large active regions that might produce solar flares or coronal mass ejections. The acoustic power in the Sun is enormous. The total energy in the oscillations is estimated at around 10 to the 26 watts, roughly 1/10 of the Sun's total luminosity. This energy continuously cycles between kinetic energy of the oscillating gas and potential energy of compression and rarefaction. It is generated at a rate determined by the turbulence in the convection zone and damped at a rate determined by radiative and conductive losses. The balance between generation and damping determines the amplitude of each mode, and the lifetimes of modes range from hours for some high-degree modes to months for low-degree modes. Listening to recordings of solar oscillations, even when sped up dramatically, provides a unique auditory experience. The tones are not pure sine waves, but complex mixtures of harmonics. They waver and beat as different modes interfere. They slowly drift as the modes evolve. There is a sense of depth, of layers of sound superimposed, which mirrors the physical reality of waves penetrating to different depths within the star. And there is a stability, a persistence, that reflects the fact that these oscillations have been ongoing for billions of years and will continue for billions more. The sun's oscillations remind us that sound is not limited to planetary atmospheres. Wherever there is gas dense enough to support pressure waves, sound can exist. Stars support sound waves. The interstellar medium, tenuous as it is, can support extremely low-frequency sound under certain conditions. Galaxy clusters, filled with hot X-ray emitting gas, support sound waves with wavelengths spanning hundreds of thousands of light-years and periods extending to tens of millions of years. Sound, in its various manifestations, is a fundamental way that energy propagates through the universe. For relaxation purposes, the sped-up recordings of solar oscillations offer something distinct. They are not musical in the traditional sense. They do not follow chord progressions or rhythmic patterns designed to evoke emotion. They are simply the acoustic signature of a physical process translated into audible form. This gives them a neutrality, an impersonality that can be deeply restful. There is no subtext, no hidden meaning, no intent. The sun vibrates according to physical law, and we are simply listening to the result. Earth is surrounded by an invisible shield, a magnetic field extending tens of thousands of kilometers into space. This field deflects the solar wind, the stream of charged particles continuously flowing from the sun. The interaction creates a structured region called the magnetosphere, shaped like a teardrop with a blunt nose facing the sun and a long tail streaming away in the anti-solar direction. Within this magnetosphere, plasma waves of various types propagate, creating sounds that spacecraft have been recording since the 1960s. The first space sounds from Earth's magnetosphere were actually detected before spacecraft existed. In the late 19th and early 20th centuries, engineers working on long-distance telephone and telegraph lines occasionally heard strange whistling sounds, especially during and after thunderstorms. These sounds descended in pitch over the course of a second or two. For decades, their origin remained mysterious. Some speculated they were atmospheric phenomena. Others thought they might be artifacts of the electrical equipment itself. The truth, eventually revealed through theoretical work and spacecraft observations, was far more interesting. These whistlers, as they came to be called, were electromagnetic waves generated by lightning strikes. When lightning discharges, it creates a burst of electromagnetic energy containing a broad range of frequencies. Some of this energy escapes into the magnetosphere, where it propagates along magnetic field lines as whistler mode waves. These waves can travel from one hemisphere to the other, guided by the field lines like waves on a stretched string. The key to understanding the descending pitch is wave dispersion. In the magnetized plasma of the magnetosphere, different frequencies travel at different speeds. Higher frequencies propagate faster than lower frequencies. When a burst of energy containing many frequencies enters the magnetosphere, the different frequency components separate over distance. If the burst originated in the northern hemisphere and you detect it in the southern hemisphere, the higher frequencies arrive first, creating a high-pitched tone that gradually drops in frequency as lower frequency components arrive later. The resulting whistle can last 1 to 2 seconds and drop in pitch by several octaves. Modern spacecraft detect whistlers regularly. The twin Van Allen probes, which orbited Earth through the radiation belts from 2012 to 2019, carried instruments specifically designed to measure these plasma waves. The Electric and Magnetic Field Instrument Suite and Integrated Science, or EMPHISIS, included antennas and sensors to detect electric and magnetic field variations from 50 Hz to 12 MHz for electric fields, and from 10 Hz to 12 kHz for magnetic fields. The resulting audio files capture whistlers in detail, often revealing multiple whistlers overlapping, creating an eerie descending chorus. Whistler mode waves are important because they interact with charged particles in the radiation belts. Earth's radiation belts are donut-shaped regions filled with energetic electrons and protons trapped by the magnetic field and bouncing back and forth between the northern and southern hemispheres. These particles pose a hazard to satellites and astronauts. Understanding how they are accelerated to high energies and how they are eventually lost from the belts is crucial for protecting space infrastructure. Whistler mode waves can scatter particles, changing their trajectories. Depending on the wave characteristics and the particle energies, this scattering can either accelerate particles to higher energies or cause them to precipitate into the atmosphere where they are lost. The balance between acceleration and loss determines how particle populations in the radiation belts evolve over time. Observations show that Whistler mode waves play a dominant role in this process. Another important type of Whistler mode wave is called chorus. Chorus emissions occur outside the dense plasmasphere in the more tenuous plasma of the outer magnetosphere. They sound like rising tones, the opposite of whistlers, or like chirps of birds. The name chorus was chosen because early observers thought the sounds resembled a dawn chorus of birds singing. The emissions typically occur at frequencies from hundreds of hertz to several kilohertz, right in the middle of the human hearing range. Chorus waves are generated through a resonant instability involving energetic electrons. When electrons bounce along magnetic field lines, they gyrate around those lines at a frequency called the electron-cyclotron frequency. This frequency depends on the local magnetic field strength. Near the magnetic equator, where the field is weakest, the cyclotron frequency is lowest. Electrons with energies of tens of kiloelectron volts can have velocities that bring them into resonance with electromagnetic waves at frequencies near the cyclotron frequency. Under the right conditions, this resonance extracts energy from the electrons and amplifies the waves, creating the chorus emissions. The rising tones of chorus result from a non-linear process. As the wave grows, it interacts more strongly with the resonant electrons, trapping them in the wave potential. These trapped electrons move along with the wave, and as the wave propagates away from the equator toward higher latitudes, the magnetic field strength increases, raising the local cyclotron frequency. The wave frequency follows this increase, creating a rising tone. The process is highly efficient, and individual chorus elements can grow to large amplitudes very quickly within fractions of a second. Chorus emissions are most intense on the dawn side of the magnetosphere in the hours after midnight local time. They occur in discrete bursts, each lasting a fraction of a second, with rising tones that can sweep from a few hundred hertz to several kilohertz. The emissions cluster into bands separated by half the local electron-cyclotron frequency, creating a characteristic two-band structure. Observations from the Van Allen probes showed that chorus can accelerate electrons to very high energies into the mega-electronvolt range in just hours to days. This makes chorus one of the primary mechanisms for creating the outer radiation belt. Inside the plasmasphere, a different type of Whistler mode emission dominates, called plasmaspheric hiss. Hiss sounds like radiostatic, a continuous noise spanning a broad frequency range, typically from hundreds of hertz to several kilohertz. Unlike chorus, which occurs in discrete bursts, hiss is steady and unstructured. The source of hiss has been debated. Some scientists think it originates from chorus waves that leak into the plasmasphere and are somehow transformed. Others think it is generated locally by different instabilities. Recent observations suggest both mechanisms may contribute depending on conditions. Plasmaspheric hiss plays a critical role in cleaning out the radiation belts. It scatters electrons, causing them to precipitate into the atmosphere. Over time, hiss continuously removes lower energy electrons from the inner belt, maintaining a relatively stable population. When the plasmasphere expands or contracts in response to geomagnetic activity, the region affected by hiss also changes, altering the loss rates of radiation belt particles. This makes understanding hiss important for predicting radiation belt dynamics. Another fascinating emission from Earth's magnetosphere is auroral kilometric radiation, or AKR. This is a powerful radio emission produced in the auroral zones at altitudes between 3,000 and 20,000 kilometers. The frequencies range from 50 kHz to several hundred kHz, well above the human hearing range, but when shifted down by a factor of several hundred, the result sounds like a series of chirps and bursts, mechanical and rhythmic. AKR is generated through the cyclotron-Massa instability, the same process that produces radio emissions from Jupiter and Saturn. Energetic electrons flowing along magnetic field lines into the auroral regions become unstable, amplifying electromagnetic waves at frequencies near the local electron cyclotron frequency. The power output can reach several billion watts, making AKR one of the most powerful natural radio sources in the inner solar system. Spacecraft beyond Earth's orbit can detect AKR, providing a way to remotely sense geomagnetic activity. The magnetosphere also produces ultra-low frequency oscillations, called ULEF waves, with periods ranging from seconds to tens of minutes. These waves involve the entire magnetosphere oscillating, the magnetic field lines swaying back and forth like plucked strings. Solar wind pressure pulses can excite these oscillations, as can sudden changes in the solar wind conditions. Different field lines have different natural frequencies depending on their length and the plasma density along them, so the magnetosphere rings like a complex musical instrument with many strings of different lengths. When spacecraft measure these ULF oscillations and convert them to audio, the result is often a slow, pulsing tone, sometimes rhythmic, sometimes irregular. The frequencies are low enough that the audio remains in the deep bass range even without shifting. Listening to these recordings, you can almost feel the magnetosphere breathing, expanding and contracting in response to external forces. It is a reminder that Earth's magnetic environment is not static, but constantly responding to the ever-changing solar wind. The solar wind itself creates a standing shockwave upstream of Earth's magnetosphere called the bow shock. When the supersonic solar wind encounters Earth's magnetic field, it cannot move past unimpeded. It slows down abruptly at the bow shock, converting its bulk kinetic energy into heat and turbulence. This transition region is filled with electromagnetic waves of all types, from ultra-low frequency waves to high-frequency plasma oscillations. Spacecraft crossing the bow shock record sudden changes in wave activity, with bursts of noise and tones appearing as the instruments pass through turbulent plasma. The magnetopause, the outer boundary of the magnetosphere, is another region of intense wave activity. Here, the pressure of the solar wind compresses the magnetosphere, creating a thin boundary layer where solar wind plasma and magnetospheric plasma interact. Magnetic reconnection events can occur at the magnetopause, where magnetic field lines from the solar wind and the magnetosphere merge, explosively releasing energy and accelerating particles. These events generate bursts of electromagnetic waves, creating sudden increases in wave intensity that spacecraft can detect. During geomagnetic storms, when the solar wind is particularly strong, or when it carries magnetic fields oriented opposite to Earth's field, the magnetosphere compresses and wave activity intensifies throughout. Chorus emissions become more frequent and intense. Hiss levels increase. ULF oscillations grow in amplitude. The radiation belts swell with newly accelerated particles. The entire magnetosphere becomes a cauldron of electromagnetic activity, and spacecraft instruments record a dramatic increase in the volume and variety of sounds. Yet even during quiet times, the magnetosphere is never truly silent. There's always some level of wave activity, some plasma oscillating, some particles gyrating, and generating electromagnetic emissions. The magnetosphere is a living, dynamic system, continuously responding to external drivers and internal processes. Listening to recordings from this environment, you hear this dynamism, the constant ebb and flow of energy, the interplay of different wave types and frequencies. For purposes of relaxation, magnetospheric sounds offer a quality distinct from solar oscillations. They are more varied, more dynamic, with sudden events and gradual changes. Whistlers drop in pitch unpredictably. Chorus chirps rise and fall at irregular intervals. Hiss provides a steady background, like rain on a roof. The combination creates a soundscape that is neither monotonous nor chaotic, holding attention without demanding it, providing structure without rigidity. The magnetosphere also connects Earth to space in a tangible way. The lightning that generates whistlers starts in our atmosphere. The waves propagate through space, thousands of kilometers away, and return to Earth on the other side of the planet. The electrons that create chorus start in the solar wind, travel through the magnetosphere, become trapped in the radiation belts, and eventually participate in wave-particle interactions that we can hear. Every emission tells a story of connection, of energy and matter flowing between different regions, of Earth embedded in the larger space environment. This connectivity extends beyond Earth. Every planet with a magnetic field has a magnetosphere, and every magnetosphere generates plasma waves. The physics is universal. The details differ, scales change, frequencies shift, but the fundamental processes remain the same. By studying Earth's magnetosphere, we learn principles that apply to other planets, to the solar wind, to the interstellar medium, to astrophysical plasmas throughout the universe. In August of 2012, the Voyager 1 spacecraft crossed a boundary that no human-made object had ever reached before. It left the heliosphere, the bubble of space dominated by the sun's influence, and entered the interstellar medium, the space between stars. 5 years later, in November of 2018, Voyager 2 followed, crossing the boundary at a different location and providing additional data about this transition. Both spacecraft carry instruments to measure plasma waves, and the sounds they have recorded from interstellar space reveal a region that, while still incredibly tenuous, is far from silent. The heliosphere forms because the sun continuously emits the solar wind, a stream of charged particles flowing outward at hundreds of kilometers per second. This wind inflates a bubble around the solar system, pushing back against the pressure of the interstellar medium. The boundary where the solar wind slows down to subsonic speeds is called the termination shock. Voyager 1 crossed this shock in 2004 at a distance of 94 astronomical units from the Sun, where 1 astronomical unit equals the distance from Earth to the Sun, about 150 million kilometers. Beyond the termination shock lies the heliosheath, a region of still outward-flowing but subsonic solar wind. This region extends outward until the solar wind pressure balances the pressure of the interstellar medium at the heliopause, the true boundary of the heliosphere. Voyager 1 reached the heliopause in 2012 at 121 astronomical units, and Voyager 2 reached it in 2018 at 119 astronomical units. The difference in distances reflects the asymmetry of the heliosphere, compressed on the side facing the direction of the Sun's motion through the galaxy and stretched out into a long tail on the opposite side. The plasma wave instrument on Voyager, called the Plasma Wave System, or PWS, consists of electric antennas and a radio receiver covering frequencies from 10 Hz to 56 kHz. These frequencies fall, mostly within the range of human hearing, or just above it, making the Voyager audio particularly direct. Unlike instruments that require significant frequency shifting, the Voyager recordings can often be played back with minimal processing. In the Helios sheath, the Voyager spacecraft detected plasma oscillations at frequencies between 2 and 3 kHz. These oscillations corresponded to electron densities of about 50 to 70 electrons per cubic centimeter, much lower than typical planetary magnetosphere densities, but still substantially higher than the interstellar medium. The oscillations were intermittent, appearing in bursts lasting days to weeks, associated with shocks and interaction regions propagating outward from the Sun. When Voyager 1 crossed the heliopause, the plasma oscillations suddenly jumped in frequency. The first detection of interstellar plasma came in October and November of 2012, when the instrument recorded oscillations at 2.6 kHz. Then, in April and May of 2013, even stronger oscillations appeared at 2.8 to 3 kHz. These frequencies corresponded to electron densities of about 80 to 90 electrons per cubic centimeter, higher than the Helios sheath values and consistent with theoretical expectations for the local interstellar medium. The source of these oscillations is not random noise, but rather the response of the plasma to disturbances propagating outward from the heliosphere. These disturbances, perhaps shock waves from solar transients that have traveled all the way to the heliopause, compress the interstellar plasma, exciting electron plasma oscillations. The spacecraft then detects these oscillations as tones at frequencies determined by the local electron density. In 2017, Voyager 1 detected another burst of oscillations, this time at frequencies around 3.1 kHz, indicating a slight increase in density. These emissions lasted several months. Then in 2020 and 2021, even more prolonged emissions appeared, allowing scientists to study the interstellar plasma in unprecedented detail. The emissions revealed that the electron density has been slowly increasing as Voyager moves away from the heliopause, rising from about 80 electrons per cubic centimeter near the boundary to over 120 electrons per cubic centimeter farther out. This increase makes sense. The heliosphere carves out a cavity in the interstellar medium, and near the boundary, the interstellar plasma is compressed and heated by the interaction. Farther from the boundary, the plasma gradually transitions to its undisturbed state. The Voyager observations are the first direct measurements of this transition, providing crucial data for understanding how the Sun's sphere of influence ends and true interstellar space begins. Voyager 2's crossing provided complementary information. Unlike Voyager 1, which crossed at a location toward the heliosphere's nose, Voyager 2 crossed farther toward the flank. The plasma conditions were somewhat different, with the initial interstellar oscillations appearing at about 3 kHz, corresponding to electron densities around 100 electrons per cubic centimeter. This is denser than Voyager 1 encountered, reflecting either temporal variability in the interstellar medium or spatial differences in density. When you listen to recordings of these interstellar oscillations, shifted slightly if necessary to bring them fully into the audible range, they sound like steady tones, sometimes pure, sometimes with slight beating or modulation. The tones last for weeks or months, slowly drifting in frequency as the density changes slightly. They are not dramatic. They do not swoosh or crackle like some magnetospheric emissions. They are simply the fundamental response of the interstellar plasma to being disturbed, a nearly pure electron plasma oscillation with minimal complication from magnetic fields or ion dynamics. The frequencies involved, a few kilohertz, correspond to wavelengths of tens to hundreds of kilometers in the plasma. These are the characteristic scales of collective behavior in this environment. Individual electrons, gyrating and bouncing around, create at these scales a coherent response, a collective oscillation that can propagate as a wave. It is a remarkable example of how enormous numbers of particles, each following simple physical laws, organize into complex, large-scale structures and behaviors. Beyond the plasma oscillations, Voyager also detects occasional bursts of radio emission, the tail end of solar radio bursts that have propagated all the way from the Sun through the heliosphere and into interstellar space. These bursts appear at frequencies between 2 and 15 kilohertz, higher than the plasma oscillations. They sound like brief, rising tones or chirps, lasting seconds to minutes. They are faint by the time they reach Voyager, attenuated by distance and scattering, but still detectable, a reminder that even in interstellar space, the Sun's influence is not entirely absent. The magnetic field in the local interstellar medium, measured by Voyager's magnetometer, has a strength of a few nanotesla, about 10,000 times weaker than Earth's surface field. This weak field still structures the plasma to some extent, influencing the propagation of waves and the behavior of charged particles. Alpha-N waves can propagate along these field lines, carrying energy and momentum. The interstellar magnetic field also deflects low-energy cosmic rays, particles accelerated to enormous speeds in distant supernova remnants and other energetic astrophysical sources. Cosmic rays create another form of sound, though not one directly audible. When cosmic rays strike the Voyager spacecraft, they create brief electrical signals in the detectors. These signals, if played as audio, sound like clicks or pops, random and irregular. The rate of these clicks increases or decreases depending on solar activity. When the Sun is active, its stronger magnetic fields deflect more cosmic rays, reducing the count rate at Voyager. When the Sun is quiet, more cosmic rays reach the spacecraft. This modulation creates a slow rhythm, a beat measured in years, corresponding to the 11-year solar cycle. The journey of the Voyager spacecraft illustrates a broader point about the universe. It is not empty. Even in the vast spaces between stars, there is plasma, magnetic fields, waves, particles. The density is incredibly low by terrestrial standards, but it is not zero. And where there is plasma, there are plasma oscillations. Where there are particles and fields, there are waves. The universe is filled with these phenomena, occurring at all scales, from planetary magnetospheres to the intergalactic medium. Listening to the sounds from interstellar space brings a sense of profound distance. These are recordings from a place more than 20 billion kilometers from Earth, farther than any human eye can see without a telescope, farther than any human will travel in the foreseeable future. The signals took 19 hours to travel back to Earth at the speed of light. The environment is one of extreme cold, near absolute zero, and extreme isolation, with the nearest star besides the Sun over 4 light-years away. Yet, it is not silent. It vibrates with plasma oscillations excited by disturbances from the Sun, with magnetic waves carrying energy through the medium, with the constant flux of cosmic rays from across the galaxy. For relaxation, these interstellar tones offer something unique. They are the farthest sounds humans have ever recorded, the most remote vibrations we have ever detected. There is a philosophical quality to listening to them, an awareness of connection across vast distances, of the spacecraft as an emissary, still sending back data, still functioning after more than 4 decades in space. The tones are simple, almost meditative in their purity, sustained notes with little variation, a sonic expression of the near uniformity of the interstellar medium. Jupiter is the largest planet in the solar system, with a mass more than twice that of all other planets combined. Its immense size is matched by the strength of its magnetic field, which is about 20 times stronger than Earth's at the planet's cloud tops and extends millions of kilometers into space. This powerful magnetosphere creates the most intense natural radio emissions in the solar system outside the Sun, emissions that can sometimes be detected by sensitive radio telescopes on Earth. Spacecraft visiting Jupiter have recorded these emissions in detail, revealing a complex and dynamic electromagnetic environment. The discovery of Jovian radio emissions dates back to 1955, when radio astronomers using equipment at the Carnegie Institute's Department of Terrestrial Magnetism detected bursts of radio noise coming from the direction of Jupiter. Initially, the bursts were puzzling. Jupiter was known to be a gas giant, but why would it produce radio emission? Theoretical work soon explained the observations. A rapidly rotating planet with a strong magnetic field can generate intense radio emissions through the cyclotron-Marsden instability, the same process that produces auroral kilometric radiation at Earth. Jupiter's radio emissions fall into several categories, distinguished by their frequency ranges and characteristics. The lowest frequency emissions, below 40 MHz, are called decometric emissions. These were the first to be discovered and remain the most dramatic, producing bursts that can last seconds to minutes and reach enormous power levels, sometimes exceeding 10 to the 13 watts. The frequencies correspond to the electron-cyclotron frequency in Jupiter's auroral regions, where the magnetic field strength is several hundred microtesla. Decometric emissions are strongly modulated by Jupiter's rotation. The planet rotates once every 9 hours and 55 minutes, one of the fastest rotation rates for any planet. As the planet spins, different regions of the magnetosphere come into view, and the radio emissions brighten and fade accordingly. Early observers noticed that the emissions occurred preferentially at certain rotational phases, leading to the realization that specific regions of Jupiter's magnetosphere were responsible. The connection to Io, Jupiter's innermost large moon, provides another modulation. Io orbits Jupiter at a distance of about 420,000 kilometers, well within the magnetosphere. Io is volcanically active, the most volcanically active body in the solar system, and its volcanoes eject sulfur and oxygen, which become ionized and form a torus of plasma around Jupiter. This Io plasma torus is one of the densest plasma regions in the outer solar system, with ion densities reaching thousands per cubic centimeter. As Io moves through Jupiter's magnetic field, it generates electrical currents connecting the moon to the planet's ionosphere. These currents, carrying millions of amperes, drive instabilities that produce intense radio bursts. Observations show that decometric emissions are much stronger when Io is at certain positions in its orbit, particularly when it is near particular longitudes relative to Earth. This Io-controlled emission pattern allowed early radio astronomers to study Jupiter's magnetic field orientation and rotation rate before spacecraft visited the planet. Higher in frequency are the hectometric emissions, spanning about 100 kHz to a few megahertz. These emissions originate closer to Jupiter in the middle magnetosphere. They are less intense than decometric emissions, but more continuous, producing a broader, more sustained signal. when converted to audio after significant frequency downshifting. Hectometric emissions sound like a wash of noise with embedded tones, rising and falling in complex patterns. At even higher frequencies, from about 20 kHz to a few hundred kHz, lie the kilometric emissions, Jupiter's counterpart to Earth's auroral kilometric radiation. These are produced in the auroral regions by the cyclotron-Massa instability. The emissions appear as narrowband tones and broader bursts, often organized into arcs in frequency-time diagrams. When played as audio, they create a series of chirps and sweeps, mechanical and alien, quite unlike terrestrial sounds. The Juno spacecraft, which entered orbit around Jupiter in 2016, carries the WAVES instrument, designed specifically to study these radio and plasma wave emissions. WAVES can detect emissions from 50 Hz to 40 MHz, covering the full range of Jovian radio phenomena. The data have revealed new details about how the emissions are generated, how they vary with time, and how they relate to other magnetospheric processes. One remarkable finding from Juno is the detection of Whistler mode chorus at Jupiter, similar to the chorus at Earth but with Jovian characteristics. The Jupiter chorus occurs at frequencies from a few hundred Hz to several kilohertz and appears in discrete rising tones, just like Earth's chorus. The emissions are associated with energetic electrons in Jupiter's radiation belts, which are far more intense than Earth's due to Jupiter's stronger magnetic field and larger magnetosphere. Listening to Jupiter chorus reveals the universal nature of these plasma wave processes, occurring wherever energetic electrons interact with magnetized plasma. Jupiter's magnetosphere also produces Whistler mode hiss, low-frequency electromagnetic noise filling the inner magnetosphere. The hiss provides a constant background against which other emissions stand out. It plays a role in scattering and precipitating particles from the radiation belts, similar to its role at Earth, but adapted to Jupiter's much harsher radiation environment. The intensity of Jupiter's radiation belts exceeds Earth's by factors of thousands, creating a region where spacecraft electronics must be heavily shielded to survive. The magnetodisk, a vast sheet of plasma extending across Jupiter's equatorial plane, contributes its own characteristic emissions. This disk forms because Jupiter's rapid rotation flings plasma outward, and magnetic field lines, unable to slip through the highly conductive plasma, are dragged along, forming a flattened disk structure. The plasma in this disk interacts with magnetic field perturbations, generating ultra-low frequency waves and ion cyclotron waves. These waves, when detected by spacecraft, can be shifted into audible range, producing slowly varying tones that reflect the motion of plasma in this enormous rotating structure. Jupiter's moons beyond Io also play roles in the magnetospheric dynamics. Europa, Ganymede, and Callisto all orbit within or near the magnetosphere, and they interact with the surrounding plasma. Ganymede, uniquely among moons, has its own magnetic field, creating a mini-magnetosphere embedded within Jupiter's larger magnetosphere. This creates complex boundary regions where waves and currents are generated. Future missions to the Jupiter system will undoubtedly reveal more about these moon-magnetosphere interactions and the sounds they produce. When listening to audio compilations of Jovian radio emissions, you hear an environment that is vastly more energetic than Earth's magnetosphere. The emissions are louder, more varied, more intense. They crackle and burst, sweep and whistle, drone and hum. There is a sense of power, of immense energies being unleashed, that reflects the reality of Jupiter's electromagnetic environment. This is the most extreme magnetosphere in the solar system, and the sounds it produces convey that intensity. Yet for all their power, these emissions are also ordered. They follow physical laws, they respond to Jupiter's rotation, to the positions of the moons, to changes in the solar wind. They are not random. They are structured, patterned, predictable at a broad level, even if individual bursts are chaotic. This structure gives the sounds a coherence that, while intense, is not overwhelming. You can listen for extended periods without feeling assaulted, because the emissions, though strong, are not designed to provoke. They are simply the electromagnetic voice of a giant planet. Saturn, the second largest planet, possesses a magnetic field and magnetosphere distinct from Jupiter's. Saturn's field is weaker, about 20 times weaker at the cloud tops than Jupiter's, but still much stronger than Earth's. The magnetosphere extends roughly 1 million kilometers sunward and far longer in the anti-solar direction. Like Jupiter, Saturn produces intense radio emissions, but Saturn's emissions have characteristics all their own, shaped by the planet's unique features, especially its spectacular ring system. Saturn's primary radio emission is called Saturn kilometric radiation, or SKR. As the name suggests, the emission peaks at frequencies around a few hundred kilohertz, corresponding to wavelengths of about 1 kilometer. SKR is generated by the cyclotron-Marso instability in Saturn's auroral regions, where energetic electrons spiraling along magnetic field lines amplify electromagnetic waves. The mechanism is the same as for Jupiter's and Earth's auroral radio emissions, but Saturn's emission has unique temporal patterns. The most striking feature of SKR is its modulation at a period close to Saturn's rotation period. Early observations suggested that Saturn rotated once every 10 hours and 39 minutes based on the periodicity of SKR. However, later observations revealed that this periodicity drifts slowly over time, varying by a few minutes, over the course of years. This was puzzling because planetary rotation rates should be stable. The resolution came with the understanding that SKR is not directly tied to the solid body rotation of the planet, but rather to oscillations in the magnetosphere driven by complex internal dynamics. The rotation rate of Saturn's interior, determined from Cassini observations of gravitational field perturbations caused by the planet's internal structure, is 10 hours and 32 minutes. But the SKR period has varied between 10 hours and 39 minutes and 10 hours and 47 minutes over the decades of observation. This variability reflects something about the magnetosphere's dynamics, perhaps related to seasonal changes in the solar wind or to internal processes within the magnetosphere. Understanding this remains an active area of research. SKR emissions are not constant. They vary dramatically with time, sometimes intense, sometimes nearly absent. The intensity correlates with solar wind conditions, with stronger solar wind pressures producing stronger emissions. This makes sense because the solar wind compresses the magnetosphere, intensifying currents and particle acceleration in the auroral regions. SKR also shows differences between the northern and southern hemispheres, related to the tilt of Saturn's rotation and magnetic axes and to seasonal illumination differences. Cassini, which orbited Saturn from 2004 to 2017, carried the Radio and Plasma Wave Science, or RPWS, instrument. This instrument detected SKR in exquisite detail, revealing fine structure in the emissions. The radio spectrum shows narrowband features, emissions concentrated in frequency ranges only a few kilohertz wide, alongside broader emissions spanning tens of kilohertz. The narrowband emissions sound like pure tones when converted to audio, while the broader emissions sound like static or hiss with embedded tones. One of the most remarkable sounds from Saturn came during Cassini's final orbits, the grand finale. During these orbits, Cassini passed between Saturn and its rings, a region never before explored by spacecraft. The RPWS instrument detected faint Whistler mode emissions and dust impacts. The dust impacts, tiny ring particles striking the spacecraft's antennas, created brief electrical signals that sounded like pops or crackles when played as audio. These sounds revealed the presence of dust particles in the gap between the planet and the rings, particles too small to be imaged but significant enough to pose a hazard and to contribute to the complex particle environment around Saturn. Saturn's rings themselves interact with the magnetosphere in fascinating ways. The rings are composed primarily of water ice particles ranging in size from micrometers to meters. These particles are electrically charged by the absorption of plasma and by the impact of ultraviolet light. The charged ring particles interact with the magnetospheric plasma, absorbing ions and electrons and affecting the local plasma density. This creates a complex interaction region near the rings, where plasma properties change rapidly with distance from the ring plane. Cassini observations showed that when Enceladus, one of Saturn's moons, is active, ejecting water vapor and ice particles from geysers at its south pole, the material forms a vast torus around Saturn. This Enceladus torus is a source of neutral and ionized water molecules that become part of Saturn's magnetospheric plasma. The torus affects plasma wave activity, contributing to the generation of certain types of Whistler mode emissions and influencing plasma densities throughout the magnetosphere. Whistler mode chorus at Saturn, detected by Cassini, resembles Jupiter and Earth chorus, but with Saturn-specific characteristics. The emissions occur at frequencies from a few hundred hertz to a few kilohertz and appear as discrete rising tones. They are most common in the middle magnetosphere, in regions where energetic electrons interact with the plasma. The chorus at Saturn is generally weaker than at Earth or Jupiter, reflecting Saturn's weaker magnetic field and lower particle energies, but it still plays a role in scattering and accelerating particles in Saturn's radiation belts. The sounds from Saturn's magnetosphere carry a different quality than those from Jupiter. Where Jupiter's emissions are intense and bursty, Saturn's emissions are often more sustained and melodic. SKR can sound like a warbling tone, slowly rising and falling in pitch and intensity. The Whistler mode emissions sound like gentle chirps or soft whistles. Even the narrowband emissions, pure tones that would seem monotonous, vary slightly in frequency and amplitude, creating a subtle, shimmering quality. During the Cassini mission, scientists created numerous audio files from RPWS data, some covering hours or days of continuous observations. Listening to these extended recordings reveals the dynamic nature of Saturn's electromagnetic environment. There are quiet periods where only faint background hiss is audible. Then, suddenly, SKR bursts appear, filling the audio with strong tones and noise. Whistler mode chorus chirps punctuate the soundscape. Dust impacts crackle briefly. The overall effect is of a complex, evolving environment that never quite repeats itself but maintains a certain character. Saturn's magnetosphere is also shaped by the solar wind in ways distinct from Earth or Jupiter. Saturn's greater distance from the Sun means the solar wind is weaker and less dense when it reaches Saturn, but it still exerts pressure, compressing the day-side magnetosphere and stretching the night side into a long tail. Changes in solar wind conditions, such as the arrival of interplanetary shocks, trigger intensifications of SKR and changes in plasma wave activity throughout the magnetosphere. Cassini observed numerous such events, providing insight into how the magnetosphere responds to external drivers. The rings complicate the picture further. They absorb plasma, creating a relatively empty region near the ring plane. They produce dust, which spreads throughout the inner magnetosphere. They reflect and scatter radio emissions, affecting how SKR propagates out of the magnetosphere. The result is that Saturn's magnetosphere is unlike any other, shaped uniquely by the presence of the most extensive ring system in the solar system. For relaxation, Saturn's sounds offer a middle ground between Earth's and Jupiter's. They are more active and varied than the simple tones from interstellar space, but less intense and chaotic than Jupiter's powerful bursts. They are melodic without being musical, structured without being repetitive. They provide a sense of motion, of energy flowing and waves propagating, but without urgency or aggression. You can imagine them as the sounds of a vast, slow-moving environment, a magnetosphere gently breathing in and out in response to the solar wind, with rings and moons adding their own subtle contributions to the electromagnetic symphony. When we think of black holes, we often imagine them as infinitely dense points surrounded by event horizons, beyond which nothing can escape. Sound, we might assume, has no place near such objects. Yet black holes can create sound, not through emission of pressure waves in the vacuum of space, but through their interaction with the hot gas that fills galaxy clusters. These sound waves have wavelengths measured in tens of thousands of light-years and periods measured in tens of millions of years, making them the deepest notes in the universe. The Perseus galaxy cluster, located about 240 million light-years from Earth, contains thousands of galaxies bound together by gravity. Between the galaxies lies hot gas, plasma heated to tens of millions of degrees. This gas is so hot that it emits X-rays which are detected by space telescopes like the Chandra X-ray Observatory. The cluster's center is dominated by a massive elliptical galaxy, NGC 1275, which harbors a supermassive black hole at its core. In 2003, analysis of Chandra observations revealed something unexpected. The X-ray emitting gas in the Perseus cluster showed ripples, concentric rings of slightly brighter and dimmer emission surrounding the central galaxy. These ripples are density variations, regions where the gas is slightly compressed or rarefied. The spacing of the ripples is enormous, about 30,000 light-years from one peak to the next. The cause of these ripples is sound waves, pressure waves propagating through the cluster gas, driven by jets of particles and energy launched by the supermassive black hole. Supermassive black holes, those with masses millions to billions of times the Sun's mass, often accrete matter from their surroundings. As material falls toward the black hole, it forms an accretion disk, a swirling disk of hot gas. Magnetic fields in the disk can launch powerful jets perpendicular to the disk, streams of particles and energy that shoot out at nearly the speed of light. These jets can extend for hundreds of thousands of light-years, far beyond the host galaxy itself. When the jets plow into the surrounding cluster gas, they create cavities, bubbles of low-density plasma pushed aside by the jet material. These cavities are visible in X-ray images as dark regions, deficits of emission. As the jets pulse or vary in strength over millions of years, they create a series of cavities at different distances from the black hole. The formation and expansion of these cavities launch sound waves into the cluster gas, the gas compressing and expanding in response to the changing pressure from the jets. The sound waves in Perseus have wavelengths corresponding to a frequency of about 10 million year periods. To convert this to a musical note, we must shift the frequency up by many, many octaves. NASA scientists calculated that the sound wave in Perseus is about 57 octaves below middle C, the lowest note on a piano. To hear it, you would need to shift it up by 57 octaves, multiplying the frequency by 2 to the power of 57, an astronomically large factor. When this is done, The resulting tone is a B flat, far below the human hearing range but representable as a musical note after the shift. This is not just a curious calculation. The sound waves carry energy, and that energy heats the cluster gas. Without this heating, the gas would cool over time, condensing and forming new stars at rates far higher than observed. The heating from the black hole jets, transmitted through sound waves and other processes, prevents runaway cooling, regulating star formation in the galaxy cluster. This is an example of black hole feedback, where the black hole influences its environment on scales thousands of times larger than the black hole itself. Other galaxy clusters show similar phenomena. The Virgo cluster, closer to us at about 50 million light-years, also shows cavities and ripples in its hot gas, driven by the central black hole in the galaxy M87. M87 is famous for being the target of the Event Horizon Telescope, which produced the first direct image of a black hole's shadow in 2019. The black hole is also driving jets and sound waves into the cluster gas, shaping the distribution of matter over vast distances. Sonification projects have taken this concept further. NASA's Chandra X-ray Observatory team has created sonifications of various objects, including black holes and galaxy clusters. For the Perseus cluster, they mapped the ripples outward from the center, converting distance into time and the brightness of the X-ray emission into pitch and volume. The resulting audio sweeps through the ripples, creating a series of tones that rise and fall as brighter and dimmer regions pass. The effect is somewhat like slowly moving a microphone past a set of bells, ringing at different pitches. For M87, sonifications combined data from multiple telescopes. X-ray data from Chandra showed the hot gas and the jet extending from the black hole. Optical data from the Hubble Space Telescope showed the galaxy's stars. Radio data showed synchrotron emission from high-energy particles. Each wavelength was mapped to a different pitch range, creating a multi-layered sonification where you can hear the different components of the system simultaneously. As the sonification sweeps across the image, the pitch and volume change to reflect the intensity of emission in each band. These sonifications are not attempting to recreate what you would hear if you were somehow present in the galaxy cluster. The frequencies involved are far too low, and the density of the gas, despite being hot, is still a near vacuum by terrestrial standards, far too tenuous to support audible sound. Instead, the sonifications are creative translations of data, attempts to make visible structures and invisible emissions accessible through hearing. They succeed in conveying scale, structure, and variation in a way that purely visual images sometimes cannot. The concept of sound in galaxy clusters extends beyond the Perseus cluster and M87. Many galaxy clusters show evidence of bubbles and cavities carved out by central black holes. These features indicate that energy is being injected into the cluster gas, and that energy must propagate somehow. Sound waves are one mechanism, though they are not the only one. Turbulence, magnetic waves, and cosmic ray pressure can all contribute. But the presence of ripples in the gas density, visible as rings in X-ray images, strongly suggests that acoustic waves are present and important. The Virgo cluster, the closest major galaxy cluster to us at about 50 million light-years, shows bubbles and filaments in its hot gas. The central galaxy, M87, has been actively feeding its supermassive black hole for a long time, perhaps billions of years. The jets from this black hole have inflated enormous bubbles, each hundreds of thousands of light-years across, pushing aside the cluster gas. As these bubbles expand and eventually rise through the cluster due to buoyancy, they launch sound waves into the surrounding medium. The cumulative effect over time is significant heat input, enough to balance cooling and maintain the cluster gas at high temperatures. The frequencies of sound waves in galaxy clusters are among the lowest in the universe. With wavelengths of tens of thousands of light-years, the corresponding frequencies fall in the range of once every 10 million years to once every 100 million years. These are periods longer than the entire history of the human species. The notes are so low that even after shifting them up 57 octaves or more to bring them into audible range, they represent only a tiny fraction of the actual wave period. It is a humbling reminder of the scales on which the universe operates. Listening to sonifications of black hole environments provides a form of contemplation distinct from listening to recordings of plasma waves or planetary sounds. These are not ongoing processes that you could monitor in real time, even if you had sensitive enough instruments. These are processes that unfold over millions of years, captured in snapshots and then translated into sounds that compress eons into seconds. They are less immediate, more abstract, but no less grounded in physical reality. Each tone corresponds to a density wave, a region of slightly compressed gas, a pressure variation that will persist for tens of millions of years before dissipating. For relaxation purposes, the sonifications of black holes and galaxy clusters offer something contemplative and almost meditative. The sounds are smooth, evolving slowly without sharp transients or sudden changes. They suggest processes operating on scales so vast that human concerns become infinitesimally small by comparison. There is comfort in that perspective, in recognizing that the universe contains structures and processes utterly indifferent to our existence, operating according to physical laws that have remained constant for billions of years and will continue for billions more. Until recently, all space sounds were indirect, translations of electromagnetic signals or density waves into audible frequencies. But in February of 2021, that changed. NASA's Perseverance rover landed on Mars carrying 2 microphones, making it the first spacecraft to directly record sounds on another planet using dedicated audio equipment. The recordings that followed provided humanity's first opportunity to hear what another world truly sounds like. Mars has an atmosphere, unlike the vacuum of space, where most electromagnetic space sounds originate. But it is a very thin atmosphere, less than 1% the pressure of Earth's atmosphere at sea level. The atmospheric composition is also different, 95% carbon dioxide compared to Earth's nitrogen-oxygen mix. These differences affect how sound propagates. Sound waves travel slower on Mars, about 240 meters per second compared to 340 meters per second on Earth. Higher frequency sounds are attenuated more strongly, meaning they do not travel as far. The result is that Mars sounds quieter and more muffled than Earth. The Perseverance rover carries 2 microphones with different purposes. One is mounted on the side of the rover's chassis, part of the entry, descent, and landing system. It is a commercial off-the-shelf microphone, selected for its durability and ability to withstand the harsh landing sequence. While it did not capture audio during the actual landing, it survived and has since recorded many hours of sounds from the Martian surface, including the rover's wheels crunching over rocks and the whirring of internal mechanisms. The second microphone is part of the SuperCam instrument, which sits atop the rover's mast. SuperCam uses a laser to vaporize small amounts of rock at distances up to about 7 meters, then analyzes the light emitted by the vaporized material to determine the rock's composition. The microphone records the sound of the laser hitting the rock, a sharp crack that varies depending on the rock's hardness and composition. Scientists have recorded more than 25,000 such laser zaps, and the variations in sound provide additional information about the rocks being studied. The The SuperCam microphone also records ambient sounds, particularly wind. Wind is the dominant natural sound on Mars, at least in the regions where Perseverance has explored. The thin atmosphere and low pressure mean that wind sounds different than on Earth. It is quieter, more of a gentle rustling than a roar. The microphone has captured wind speeds ranging from a few meters per second to over 15 meters per second, with the sound varying accordingly. During dust devils, small whirlwinds that frequently cross the Martian surface, the microphone records sudden increases in wind noise and changes in pressure that can be correlated with pressure sensor data. One particularly remarkable recording came in September of 2021, when a dust devil passed directly over the rover. The microphone captured the sound of wind increasing as the vortex approached, peaking as it passed overhead, and then decreasing as it moved away. The recording lasted only a few seconds, but provided the first direct audio recording of a Martian dust devil. Scientists compared the audio to pressure and temperature measurements from other instruments, building a more complete picture of how these atmospheric phenomena behave. Another set of recordings comes from the Ingenuity helicopter, a small rotorcraft that demonstrated the first powered flight on another planet. Ingenuity flew over 40 times during its mission, and on several occasions, Perseverance was positioned to record the sound of the helicopter flying. The sounds are faint due to the thin atmosphere and the distance between the rover and the helicopter, typically over 80 meters. But with careful processing, isolating the frequency of the helicopter's rotor blades at 84 Hz, the hum of Ingenuity can be heard against the background wind noise. These recordings are significant because they demonstrate that sound propagates on Mars in measurable ways, and that microphones can serve as scientific instruments for studying atmospheric dynamics. The speed of sound on Mars, measured by timing how long it takes the sound of laser impacts to reach the microphone from known distances, confirmed theoretical predictions of about 240 meters per second. The attenuation of different frequencies, measured by comparing sounds at different distances, provided data on how the atmosphere absorbs sound energy. The sounds themselves are gentle, even soothing. The wind is a soft whoosh, never harsh or overwhelming. The laser zaps are brief pops, interesting but not startling. The rover's wheels produce a rhythmic crunching, metal against rock, mechanical but not unpleasant. When played back without narration or music, these recordings offer a sense of what it would be like to stand on the surface of Mars, listening to the wind and the occasional rattle of a rover driving past. Mars is quieter than Earth in several ways. There are no oceans, so no crashing waves. There are no forests, so no rustling leaves or bird calls. There is no rain, at least not in liquid form, though there are occasional snowfalls of frozen carbon dioxide at the poles. The dominant sounds are wind, dust impacts, and occasionally the rumble of avalanches on steepy slopes, though those have not been recorded directly. It is a sparse soundscape, minimalist in its composition, which gives it a peaceful quality. The recordings also convey a sense of remoteness. These sounds were captured on a world more than 100 million kilometers from Earth at the time of recording, sometimes over 300 million kilometers, depending on the relative positions of Earth and Mars in their orbits. The signals took between 3 and 22 minutes to travel from Mars to Earth at the speed of light. When you listen to sounds from Mars, you are hearing an environment that no human has ever directly experienced, that no human ear has ever occupied. It is alien, yet familiar, distant, yet comprehensible. For purposes of relaxation, Martian sounds offer something unique. They are actual sounds from another world, not translations or sonifications, but direct audio recordings. They are gentle, repetitive in the case of wind, and sparse with long stretches, where little changes. The wind provides a form of natural white noise, masking other sounds and creating a consistent background. The occasional rover noise adds variation without disruption. The overall effect is peaceful, conducive to rest, and filled with the subtle wonder of experiencing another planet through sound. Scientists have noted that listening to audio from Mars sometimes reveals features not immediately apparent in other data. Variations in wind speed can be heard as changes in the volume and pitch of the wind noise. The passage of atmospheric structures, like pressure fronts or vortices, can be detected as shifts in the sound character. This has led to proposals for future Mars missions to include more sophisticated microphone systems, possibly arrays of microphones that could provide directional information and help locate sound sources more precisely. The success of the Perseverance microphones has also inspired discussions about including microphones on future missions to other bodies with atmospheres such as Venus or Titan. Venus has an incredibly thick atmosphere, 90 times the pressure of Earth's, which would make it an extremely loud environment, with wind sounds and possibly thunder from volcanic lightning. Titan, Saturn's largest moon, has a thick atmosphere primarily composed of nitrogen and methane, with methane rain and possibly methane oceans. The sounds on Titan would be very different from Mars, likely louder and with more varied sources. But for now, Mars is the only other world where we have direct audio recordings, and those recordings provide a gentle, contemplative soundscape that connects us to another planet in a tangible way. Beyond the direct recordings from Mars and the electromagnetic emissions from magnetospheres and interstellar space, there exists another category of space sounds. Sonifications of data collected by telescopes observing in wavelengths beyond human perception. These sonifications are not sounds that exist in nature. They are creative translations, mappings of brightness, color, position, and time into pitch, volume, timbre, and rhythm. They represent a fusion of science and art, designed to make astronomical data accessible through hearing and to reveal patterns that might not be apparent through vision alone. The process of sonification begins with data, typically images captured by space telescopes such as the Hubble Space Telescope, the James Webb Space Telescope, or the Chandra X-ray Observatory. These images show light across the electromagnetic spectrum, from radio waves through infrared, visible light, ultraviolet, and X-rays. Much of this light is invisible to human eyes. Even visible light images are often created by combining observations through different filters and assigning colors to represent different wavelengths or physical conditions. To sonify an image, scientists and sound designers decide how to map visual properties to auditory properties. Brightness might be mapped to volume, so brighter regions sound louder. Position might be mapped to pitch, so features at the top of an image produce higher notes than features at the bottom. Color might be mapped to timbre, so different wavelengths are represented by different instruments or synthesized sounds. Time, if the sonification moves across the image, might correspond to the progression of the music. Consider the sonification of the Crab Nebula, a supernova remnant located about 6,500 light-years away in the constellation Taurus. The Crab Nebula was created by a star that exploded in the year 1054, observed by astronomers in China and elsewhere as a brilliant new star visible in daylight for weeks. Today, the nebula is an expanding cloud of gas and dust, powered by a rapidly spinning neutron star, or pulsar, at its center. This pulsar rotates about 30 times per second, emitting beams of radiation that sweep across space like a cosmic lighthouse. Images of the Crab Nebula combine data from multiple telescopes. X-rays from Chandra show the most energetic regions, where particles accelerated by the pulsar emit high-energy light. Optical light from Hubble reveals the filaments of gas expanding outward from the explosion. Infrared light from the Spitzer Space Telescope highlights warm dust. In the sonification, each wavelength is assigned to a different family of instruments. X-rays are represented by brass, optical light by strings, and infrared by woodwinds. As the sonification scans from left to right across the image, the pitch changes based on vertical position, and the volume changes based on brightness. The result is a layered, evolving piece of music. The bright pulsar at the center produces a loud, multi-timbral sound as all wavelengths are present. The jets extending from the pulsar create sweeping changes in pitch and timbre. The filaments of gas produce complex interweaving melodies as the scan passes over regions of varying brightness. The entire sonification lasts about a minute, compressing the spatial structure of a light-year-scale nebula into a brief auditory experience. Another notable sonification is that of the center of the Milky Way galaxy. This region, located about 26,000 light-years from Earth, contains the supermassive black hole Sagittarius A star, which has a mass of about 4 million times the Sun's mass. Surrounding the black hole are dense clouds of gas and dust, regions of star formation, and the remnants of past stellar explosions. Observations from Chandra reveal hot gas heated to millions of degrees. Hubble shows stars and dust lanes. Spitzer reveals glowing infrared emission from complex molecules. The sonification of the galactic center scans from left to right, with vertical position mapped to pitch and brightness mapped to volume. Stars appear as individual notes, brief and distinct. The extended clouds of gas produce sustained tones that evolve as the scan moves through brighter and dimmer regions. The crescendo occurs when the scan reaches the region near Sagittarius A star, where the gas is brightest and the X-ray emission is most intense. The soundscape conveys the crowded, energetic nature of the galaxy's core, a stark contrast to the relatively quiet neighborhood of our solar system in the galactic suburbs. Sonifications can also represent time evolution, not just spatial structure. The sonification of supernova 1987A, or SN87A, uses observations taken over 14 years to show how the supernova remnant brightened as the explosion's shockwave expanded outward and collided with material ejected by the star before it exploded. The sonification uses the sound of crystal singing bowls, with brightness mapped to pitch and volume. As the remnant brightens over the years represented in the data, the sound becomes louder and higher pitched, creating a sense of growth and evolution. The Hubble Ultra Deep Field, one of the most famous astronomical images, has been sonified to represent the roughly 10,000 galaxies visible in a tiny patch of sky. Each galaxy is assigned a single note, with the timing of the note corresponding to the galaxy's distance from Earth. Closer galaxies play earlier in the sonification, more distant galaxies play later. The pitch represents the galaxy's color, with redder galaxies producing lower notes and bluer galaxies producing higher notes. The volume represents the galaxy's apparent size. The result is a minute-long piece that takes you back through 13 billion years of cosmic history, from nearby galaxies formed relatively recently to the most distant galaxies, whose light was emitted when the universe was only a few 100 million years old. Sonifications serve multiple purposes. For scientists, they can reveal patterns that are difficult to see in images. The human auditory system is excellent at detecting temporal patterns, changes in pitch or rhythm, and subtle variations in timbre. A slow drift in brightness that might be missed in a static image can be immediately apparent as a rising or falling tone. Periodic variations can be heard as rhythms. Spatial correlations between different wavelengths can be perceived as harmonies or dissonances. For educators and communicators, sonifications provide a way to engage audiences who might not connect with images alone. They add an emotional dimension to the data, making abstract concepts feel more immediate and tangible. They are particularly valuable for blind and low-vision individuals, providing access to astronomical data that would otherwise be entirely visual. Studies have shown that people who experience sonifications report learning gains and express curiosity about the science behind the sounds. For the general public, sonifications offer an aesthetic experience. They are beautiful in the way that patterns of sound organized by physical relationships can be beautiful. They are not designed to be emotionally manipulative, as music composed for entertainment often is. They are neutral in their origin, the sounds determined by the data rather than by a composer's intent to evoke sadness or joy. Yet, they are not random. They have structure imposed by the universe itself, by the distribution of matter and energy, by the laws of physics. The process of creating sonifications requires collaboration between scientists who understand the data, sound designers who can translate scientific principles into auditory mappings, and accessibility experts who can ensure the final product is useful and engaging. The team that has produced most of NASA's sonifications includes astrophysicist Matt Russo, musician Andrew Santaguida, visualization scientist Kimberly Arcand, and accessibility consultant Christine Malik. Their work has resulted in dozens of sonifications representing supernova, galaxies, nebulae, black holes, and other astronomical objects. The choices made during sonification are not arbitrary, but also not unique. Different mappings would produce different sounds while representing the same data. A brightness to pitch mapping would sound different from a brightness to volume mapping. A left-to-right scan would sound different from a top-to-bottom scan or a radial scan outward from the center. The team makes choices based on what best represents the data's key features and what creates the most engaging listening experience. There is also a tension between scientific accuracy and aesthetic appeal. A sonification that perfectly represents every nuance of the data might be cluttered and difficult to listen to. A sonification optimized for beauty might obscure important details. The best sonifications strike a balance, preserving the essential structure of the data while creating something that people want to hear more than once. For relaxation, sonifications offer something between natural sounds and composed music. They are more structured than wind or ocean waves, with clear melodies and harmonies emerging from the data. But they are less predictable than conventional music, with unexpected shifts and variations driven by the actual properties of astronomical objects rather than musical conventions. They are intellectually engaging without being demanding, providing substance for the mind to explore while remaining calm enough to support rest. The variety of sonifications is also valuable. A sonification of a supernova remnant sounds different from a sonification of a galaxy collision, which sounds different from a sonification of a black hole's accretion disk. Each represents a different physical process, a different configuration of matter and energy, and thus produces a different auditory signature. You can listen to many sonifications without encountering repetition, each one revealing a new facet of the universe's structure and behavior. We have explored many types of space sounds, from the vibrations of the sun to the plasma waves of magnetospheres, from the interstellar tones detected by Voyager to the wind on Mars, from the acoustic waves in galaxy clusters to the sonifications of telescope data. Each type has its own character, its own origin, its own qualities, but many share common features that make them particularly suited to relaxation and sleep. Understanding these features helps explain why people find space sounds calming. First, Space sounds lack human emotional content. They are not created to communicate happiness or sadness, excitement or fear. They are the product of physical processes, operating according to natural laws. A plasma wave oscillates at a frequency determined by electron density and magnetic field strength, not by any intent to affect a listener. A sound wave in a galaxy cluster propagates at a speed determined by gas temperature and composition, carrying energy from a black hole's jet, but carrying no message, no meaning, no purpose, beyond the transfer of momentum and heat. This emotional neutrality is valuable for relaxation. Human-created sounds, including most music and speech, carry emotional weight. They are designed to evoke responses, to persuade or entertain, to comfort or disturb. Our brains are highly attuned to these signals, analyzing tone of voice, musical structure, word choice. Listening to human-created sounds requires cognitive engagement, conscious or unconscious processing of meaning and intent. Space sounds bypass this entirely. They simply are, indifferent to the listener, requiring no interpretation, no response. Second, space sounds operate on scales beyond human experience. The sun vibrates with periods of 5 minutes, but those oscillations have been ongoing for billions of years. The plasma in Earth's magnetosphere responds to the solar wind, which varies on timescales from seconds to days to the 11-year solar cycle, but the magnetosphere itself has existed for most of Earth's history. Sound waves in galaxy clusters take tens of millions of years to propagate. These temporal scales dwarf human concerns. Listening to sounds connected to such vast scales of time provides perspective, a reminder that most of what we worry about is fleeting and small. The spatial scales are equally vast. Voyager's instruments detect plasma waves in a region trillions of kilometers from Earth. The black hole in the Perseus cluster launches sound waves that propagate across hundreds of thousands of light years. The sun's oscillations involve movements of gas across hundreds of thousands of kilometers. These distances are incomprehensible in human terms, yet the sounds allow us to connect, however tenuously, to those scales. There is comfort in knowing that the universe operates on scales so large that our individual existence is utterly inconsequential, yet the universe is still knowable, still accessible through instruments and mathematics and sound. Third, space sounds have structure without being repetitive. Natural sounds on Earth, like ocean waves or rain, are often used for relaxation because they are consistent without being monotonous. Each wave or raindrop is slightly different, but the overall character remains the same. Space sounds share this quality. Whistler mode chorus produces chirps that rise in pitch, but each chirp is unique in its exact frequency range and duration. Saturn's kilometric radiation varies in intensity and frequency, creating a shimmering, evolving tone that never quite repeats. The wind on Mars fluctuates with gusts and lulls, each gust shaped by local topography and atmospheric conditions. This structure engages the mind just enough to hold attention without demanding full focus. It is easy to drift while listening to space sounds, to let the mind wander, to slip towards sleep. Yet if you choose to pay attention, there is always something to notice, a subtle variation, a momentary intensification, a new texture in the sound. This balance between engagement and drift is ideal for both relaxation and sleep. Fourth, many space sounds fall into frequency ranges and volumes that are naturally calming. Very low frequencies, below about 20 Hz, are felt more than heard and can be unsettling or even frightening, associated with infrasound from earthquakes or explosions. Very high frequencies, above about 15 kHz, can be grating or painful at high volumes. The middle range, from about 100 Hz to a few kilohertz, is where human speech and much of music occurs, and it is the range where our hearing is most sensitive and most comfortable. Many space sounds, when shifted into audible range if necessary, fall into this middle range. Chorus emissions naturally occur between a few hundred hertz and a few kilohertz. Interstellar plasma oscillations detected by Voyager are around 2 to 3 kilohertz. The sonified sun produces complex tones in the low hundreds to a few thousand hertz. These frequencies are familiar, neither threatening nor irritating, simply present. The volumes in recordings are also moderate, enough to hear clearly but not loud enough to startle or disturb. Fifth, space sounds often have a quality of continuity and flow. Unlike music, which has beginnings, middles and ends, verses and choruses, climaxes and resolutions, space sounds tend to evolve gradually without dramatic shifts. A recording of plasma waves might last for minutes or hours, with slow changes in intensity and frequency, but no sudden stops or starts. A sonification might scan across an image over a minute, with smoothly changing pitch and volume as the scan moves through regions of different brightness. This continuity supports long listening sessions. You can start listening at any point and stop at any point without feeling you have missed something important. There is also no narrative arc, no story being told. Stories engage the mind differently than pure sensory input. They create expectations, anticipation of what comes next, concern for characters or outcomes. Space sounds do not tell stories. They are events, processes, phenomena, but they are not narratives. This absence of story allows the mind to rest from the constant interpretation of meaning and intent that characterizes so much of human communication. Sixth, there is a meditative quality to the knowledge that space sounds represent something real. These are not fabricated soundscapes, not random noise generators, not abstract compositions. Every tone, every variation corresponds to an actual physical process occurring somewhere in the universe. The plasma wave exists, the electron density is real, the magnetic field has a measurable strength. For some people, this grounding in reality enhances the experience. The sounds become a form of meditation on the nature of existence, on the laws of physics, on the vastness and structure of the cosmos. Philosophical perspectives vary, but many find comfort in the regularity and predictability of natural law. The universe operates according to rules that do not change with mood or circumstance. Gravity always attracts. Electromagnetic waves always propagate at the speed of light in vacuum. Charged particles always spiral in magnetic fields. Listening to sounds that are the direct consequence of these laws can provide a sense of order and stability, a counterpoint to the unpredictability and chaos that often characterize human affairs. Seventh, space sounds are free from cultural associations and historical baggage. A piece of music might remind you of a particular time or place, evoke memories happy or sad. A particular voice might recall a person you knew. Even natural sounds can carry associations. The sound of rain might remind you of childhood, the ocean of a vacation, wind of a storm that frightened you. Space sounds, being entirely new to human experience, carry no such associations. They are fresh, unmarked by personal history or cultural meaning. This neutrality allows them to serve as a blank canvas onto which you can project calm without interference from memory or meaning. Finally, the variety of space sounds means there is something for every preference. If you prefer steady, drone-like sounds, interstellar plasma oscillations or the hum of magnetospheric hiss might appeal. If you prefer more dynamic sounds with variation and texture, chorus emissions or Saturn's kilometric radiation might be better. If you prefer sounds connected to tangible objects, recordings from Mars or sonifications of visible structures like nebulae and galaxies might resonate. The diversity ensures that space sounds can meet a wide range of relaxation and sleep needs. Research on the effects of sound on relaxation and sleep is ongoing, but some general principles are well established. Steady, predictable sounds can mask disruptive noises from the environment, creating a consistent auditory environment that supports sleep. Sounds in the frequency range of human speech can provide comfort without stimulating the language processing centers of the brain, especially if the sounds lack linguistic structure. Sounds at moderate volumes, neither too loud nor too quiet, can create a sense of presence without intrusion, a feeling of being accompanied without being crowded. Space sounds embody all of these principles. They are steady in character while varying in detail. They occupy the frequency ranges where our hearing is most comfortable. They lack linguistic content or emotional manipulation. They operate at scales of time and space that dwarf human concerns, providing perspective without preaching. And they are grounded in reality, in the measurable properties of the universe, which gives them a substance that purely abstract sounds might lack. We have traveled through many types of space sounds, each offering a unique window into processes and places beyond our direct experience. From the interior of the Sun, where acoustic waves have resonated for billions of years, to the surface of Mars, where wind whispers across ancient plains. From the magnetosphere of Earth, where plasma waves create an invisible symphony, to the edge of the solar system and beyond, where Voyager listens to the faint oscillations of interstellar space. From the mighty radio emissions of Jupiter and Saturn to the deep bass notes of black holes singing in clusters of galaxies. Each sound we have encountered is real in the sense that it corresponds to a measurable physical process. The Sun truly vibrates. The magnetosphere truly generates whistlers and chorus. Voyager truly detects plasma waves in the space between stars. Mars truly has wind. Black holes truly launch sound waves into galaxy cluster gas, and telescopes truly record light that can be translated into sound through careful mapping of brightness, color, and position. These sounds are not just curiosities, they are tools for understanding the universe. Helioseismology has revealed the Sun's internal structure with remarkable precision. Plasma wave observations have illuminated how particles are accelerated and lost in planetary magnetospheres. Interstellar measurements have quantified the properties of the local galactic environment. Wind recordings on Mars have improved our understanding of Martian atmospheric dynamics, and sonifications have made astronomical data accessible to broader audiences, including those who cannot see visual images. But beyond their scientific value, space sounds offer something for the spirit. They are invitations to contemplate scales and processes far removed from daily life. They are reminders that the universe is vast, ancient, and governed by laws that operate without regard for human desires or fears. They are opportunities to experience wonder without anthropomorphism, to appreciate the cosmos as it is rather than as we might wish it to be. The electromagnetic waves in a magnetosphere oscillate because electrons and ions respond to electric and magnetic forces. The sound waves in a galaxy cluster propagate because hot gas has pressure and density that create a medium for compression and rarefaction. The wind on Mars blows because temperature differences drive atmospheric circulation. These processes have no purpose, no goal, no meaning in a human sense. They simply occur, the inevitable consequence of matter and energy existing in configurations that allow complexity. There is a peace in that purposelessness. The universe does not demand anything of you. It does not judge, does not care, does not notice whether you succeed or fail at the tasks that occupy your days. It is utterly indifferent, and in that indifference lies a strange form of comfort. Your worries, however pressing they feel, are insignificant on cosmic scales. The black hole in Perseus will continue to launch sound waves whether you are anxious or calm, whether you are awake or asleep. This is not nihilism, not a claim that nothing matters. It is simply perspective. Human concerns matter to humans, and that is valid and important. But they do not matter to the universe, and remembering that can relieve some of the weight we carry. Listening to space sounds can be a form of cognitive reset, a way of temporarily stepping outside the frame of human society and human time, entering a frame where processes unfold over millions of years and distances span millions of light years. The sounds themselves are beautiful, though beauty in this context means something different from aesthetic pleasure derived from art. It is the beauty of pattern, of structure emerging from law, of complexity arising from simple rules applied across vast scales. It is the beauty of understanding, of hearing a tone and knowing that it represents an electron density, a magnetic field strength, a temperature, a distance. It is the beauty of connection, of sitting on Earth and hearing vibrations from the Sun, emissions from Jupiter, oscillations from beyond the solar system. And the sounds are calming, whether because of their frequency content, their lack of emotional manipulation, their grounding in reality, or simply their novelty. Space sounds provide an auditory environment that many find conducive to relaxation and sleep. They offer something consistent yet varied, substantial yet gentle, engaging yet undemanding. They are sounds to drift with, to imagine by, to rest against. As we near the end of this exploration, it is worth reflecting on how much is left unexplored. We have touched on only a fraction of the sounds that could be recorded or created from space data. There are the seismic vibrations of Mars detected by the InSight lander, which reveal the interior structure of the planet through the propagation of quakes. There are the sounds of comets, which have magnetic fields that interact with the solar wind. There are the pulses from pulsars, rapidly spinning neutron stars that sweep beams of radiation across space with extraordinary regularity. There are the gravitational waves from merging black holes and neutron stars, which have been converted to sound and heard as chirps sweeping upward in frequency. Each of these offers its own character, its own connection to physical processes, its own potential for understanding and appreciation. The universe of sound, both actual and translated, is vast and largely unexplored. What we have covered here is an introduction, a sampling, a first step into a much larger domain. But the sounds we have encountered are sufficient to illustrate the main themes. Space is not silent, not when we expand our definition of sound to include electromagnetic waves and pressure variations at all frequencies. Space is filled with vibrations, oscillations, waves of every description, operating across every scale. We can listen to these, either directly or through translation, and in listening we can connect to processes and places that would otherwise remain purely abstract. We have spent considerable time together exploring the sounds of space, moving from the sun to the edge of the solar system and beyond, from planetary magnetospheres to galaxy clusters, from electromagnetic emissions to actual atmospheric recordings, from direct observations to creative sonifications. Throughout this journey, a central theme has persisted. The universe generates patterns, and those patterns can be experienced through sound. Sound is fundamentally about vibration, about energy moving through a medium in organized ways. On Earth, that medium is typically air, and the vibrations are pressure waves. In space, the media and mechanisms differ, but the underlying concept remains. Plasma vibrates in response to electric and magnetic forces. Gas in galaxy clusters compresses and expands under pressure gradients. Data from telescopes encodes variations in brightness and position that can be mapped to variations in pitch and volume. All of these are forms of vibration, of pattern, of structure in how energy and information propagate. Experiencing these vibrations as sound provides a direct, visceral way to engage with the cosmos. Vision is our dominant sense for exploring the universe, and telescopes have revealed astonishing structures across billions of light years. But hearing adds another dimension, a way to experience temporal patterns, to detect rhythms and periodicities, to feel connections between events separated in time. Hearing is intimate in a way vision is not. Sound exists in time, unfolding moment by moment, requiring you to be present with it rather than observing it from a distance. The space sounds we have explored offer that intimacy. When you listen to chorus emissions from Earth's magnetosphere, you are experiencing, through your auditory system, the same electromagnetic waves that accelerate electrons in the radiation belts. When you hear the wind on Mars, you are connected, through a chain of technology and transmission, to the actual atmosphere of another planet, the same gas that fills ancient craters and swirls around extinct volcanoes. When you experience a sonification of a galaxy, you are engaging with light that traveled for millions of years, carrying information about stars, gas, and dust across cosmic distances. This connection is not metaphorical. It is physical, mediated by instruments and translation processes, but real nonetheless. The plasma wave existed. The instrument detected it. The data was transmitted to Earth. The audio file was created. And now, sound waves in the air around you carry a representation of that distant event to your ears. The chain is long, but it is unbroken. You are listening to the universe. There is humility in this listening. The universe was not speaking to you. It was not creating these sounds for any audience. They are byproducts, secondary effects, the unavoidable consequences of physical laws acting on matter and energy. Yet we can hear them, and in hearing them, we can understand something about how the universe works. We can measure electron densities from plasma frequencies. We can infer black hole jet power from sound wave amplitudes. We can study atmospheric dynamics from wind recordings. Sound, even when translated or created through sonification, is a carrier of information, a way of knowing. And there is also elevation in this listening, a sense that human capabilities have extended to embrace phenomena far beyond the ordinary. We have built instruments sensitive enough to detect vibrations in plasma so tenuous it is essentially vacuum. We have sent those instruments across billions of kilometers. We have developed mathematical frameworks to understand what the instruments detect. We have created technologies to convert invisible electromagnetic fields into audible sounds. We have imagined ways to represent telescope data as music. These are achievements worth contemplating, examples of human curiosity and ingenuity directed toward understanding rather than conquering. The relaxation that space sounds provide may come, in part, from this dual awareness of humility and elevation. We are small, our lives brief, our concerns temporary and local. The universe is vast, ancient, and uncaring. Yet we are capable of understanding, of listening, of finding patterns and meaning in observations. We are both insignificant and remarkable, ephemeral and part of a continuum of matter and energy that stretches back to the beginning of the universe and forward to its eventual end. Space sounds hold this paradox, expressing both the indifference of the cosmos and the capacity of consciousness to engage with it. As you continue listening, or as you drift towards sleep, consider that the sounds you hear, whether actual recordings or sonifications, represent processes that existed long before humans evolved and will continue long after our species is gone. The sun will vibrate for billions of years more. The magnetospheres of planets will continue to generate waves as long as the planets have magnetic fields and are bathed in solar wind. The interstellar medium will oscillate in response to disturbances from stars and supernovae. Black holes will launch sound waves into galaxy clusters for tens of millions of years per cycle. Mars will have wind as long as it has an atmosphere. These are not sounds created for you, but they are sounds you can experience. And in experiencing them, you participate in a larger story. The story of a universe that generates complexity from simple laws, that creates structure at every scale, that vibrates with energy in myriad forms. You are made of atoms forged in stars, listening to vibrations from other stars, other planets, other regions of space. The connection is real, tangible through sound, grounding even as it reaches toward the cosmic. The space sounds we have explored are gifts, not in the sense of being given with intent, but in the sense of being available, accessible, waiting to be discovered and shared. Scientists and engineers created the instruments. Mission planners sent them into space. Analysts processed the data. Sound designers created the sonifications. And now, these sounds are here, free to anyone who wishes to listen, offering calm, perspective, wonder, and rest. In a world filled with noise designed to manipulate attention and emotion, space sounds stand apart. They ask nothing. They promise nothing. They simply are representations of processes that would occur regardless of human presence or absence. This makes them rare and valuable. They are honest in a way that little else is, constrained by physics rather than by intent, shaped by the universe rather than by desire to persuade or entertain. If these sounds help you relax, if they carry you towards sleep, if they provide a backdrop for quiet thought, they are serving a purpose, though not one they were created for. They are serving the purpose you give them, which is to support rest, to offer an alternative to the constant churn of human communication and concern, to provide a space, both literal and figurative, where the mind can settle. And if you find yourself curious about the processes behind the sounds, if you wonder about plasma frequencies or magnetic field strengths or the mechanisms of sonification, that curiosity is welcome. Space sounds can be relaxing and educational, calming and intellectually stimulating, depending on how you choose to engage with them. They can be background noise, or they can be the focus of active listening. They can accompany sleep, or they can accompany contemplation. They are versatile in this way, adapting to your needs because they have no agenda of their own. The universe is not designed for human comfort or understanding. It simply is, operating according to laws discovered over centuries of observation and experiment. But within that indifferent vastness, there are phenomena we can detect, translate, and experience. Space sounds are among these phenomena, vibrations made audible, distances made intimate, complexity made accessible. They are a form of grace, not granted but discovered, not given but earned through effort and ingenuity. As this exploration comes to a close, remember that the sounds continue. The sun continues to vibrate. The magnetospheres continue to generate plasma waves. Voyager continues to detect interstellar oscillations, transmitting data back across billions of kilometers. Mars continues to experience wind. New telescopes continue to gather data that can be sonified. The universe continues to vibrate in countless ways, most of which we have yet to discover or translate. You can return to these sounds whenever you wish, in recordings and sonifications available online, in archives maintained by space agencies and research institutions, in projects created by scientists and sound designers who share a commitment to making the universe accessible. The sounds will be there, waiting, unchanged, as patient and enduring as the processes they represent. And perhaps, as you listen now or in the future, you will carry with you a deeper awareness of what you are hearing. Not just soothing tones or interesting noises, but echoes of real events, translations of electromagnetic fields, recordings of other worlds. Each sound is a window, a connection, a thread linking you to places and processes far beyond the immediate, the everyday, the familiar. The cosmos is vast, but it is knowable. The universe is ancient, but it is present. Space is distant, but it is audible. And in listening, we participate in something larger than ourselves, something that was here before us and will continue after, something that vibrates with structure and pattern and energy across every scale from subatomic to galactic and beyond. This is the gift of space sounds, not just calm or rest, though they provide both, but connection and perspective, intimacy with the infinite, understanding of the incomprehensible, one vibration at a time. Thank you for spending this time exploring the sounds of space together. We have covered remarkable ground, from the hidden symphony of the sun to the whispers of interstellar plasma, from the chorus of magnetospheres to the wind on Mars, from the bass notes of black holes to the translated light of distant galaxies. Each sound we encountered was rooted in scientific observation, each detail grounded in measurements taken by instruments across the solar system and beyond. If you found value in this journey, if the information helped you understand something new about how the universe generates sound, or if the calm, pacing, and detailed explanations supported your relaxation or sleep, I invite you to consider liking this video and subscribing to the Nebula Nights channel. This helps the channel continue to create long-form, detailed, scientifically accurate content about space and astronomy, all presented in this gentle, unhurried style designed to accompany your quiet hours. Subscribing means you will be notified when new videos appear, allowing you to continue exploring different aspects of the cosmos through sound and information. There are many more topics to cover, many more phenomena to explain, many more connections to draw between the universe's behavior and the ways we can experience and understand it. The universe is patient, and so is this channel. Whether you listen once or many times, whether you stay for minutes or hours, whether you remember the details or simply carry away an impression of vastness and structure, you are welcome here. This is a space for quiet learning, for gentle exploration, for rest accompanied by genuine information about the cosmos. Thank you for listening. May your rest be deep, your curiosity satisfied, and your awareness of the universe's sounds remain with you, a reminder that even in silence, the cosmos vibrates with patterns waiting to be heard. Clear skies and good night.